In this model, we will assume that each ball falls directly onto a certain central peg, and that it has a 50-50 probability of bouncing to the left or to the right. And we'll think of each of those outcomes as either adding one or subtracting one from its position. Once one of those is chosen, we make the assumption that it happens to land dead on in the middle of the peg adjacent below it, where again it'll be faced with the same 50-50 choice of bouncing to the left or to the right. So our little hopping ball makes 5 different random choices between +1 and -1, and we can think of its final position as basically being the sum of all of those different numbers, which in this case happens to be 1, and we might label all of the different buckets with the sum that they represent. If we let many different balls fall, making yet another unrealistic assumption that they don't influence each other, as if they're all ghosts, then the number of balls that fall into each different bucket gives us some loose sense for how likely each one of those buckets is. The neat thing about our theorem is how far it goes beyond the simple examples. So to start off at least, rather than making explicit calculations, let's just simulate things by running a large number of samples and letting the total number of results in each different outcome give us some sense for what that distribution looks like. And the basic idea of the central limit theorem is that if you increase the size of that sum, for example, here that would mean increasing the number of rows of pegs for each ball to bounce off, then the distribution that describes where that sum is going to fall looks more and more like a bell curve.